Newton's second law of motion states that the acceleration of an object is directly proportional to the net force acting on it. Now, let's look at that in terms of gravitational forces on objects. So for a second, let's talk about gravity. For there to be a gravitational force, there has to be at least two objects that are interacting. And we can say that we're going to look at the gravitational force of the Earth on different things. And let's consider the force of gravity on a person. And here is the equation for force of gravity. And the force of gravity is directly proportional to the mass of the two objects multiplied by each other divided by the distance between their centers of mass to the second power. And what centers of mass? Centers of mass are, for example, with the Earth, it's got some size, but you could consider that if all of its mass was centered at a point and not spread out over all of its space and volume, that if all the mass was at that point, the distance from this point, not from the surface of the Earth, not from any other spot, if you had all the mass centered there, you would have the same gravitational effect on an object, such as a person, right here on the surface of the Earth. So this R is not the distance from the person's body to the surface of the Earth, but to its centers of mass, which is, for the Earth, its mass is distributed evenly, so the center of the sphere of the Earth is its center of mass. So we say that it is proportional to that. Now, if you include in the equation this gravitational constant, which is, as you can see, it's 10 to the minus 11th. It's a very, very, very small value. But this gravitational constant, if put into this equation, makes the force of gravity an equality with the two masses involved multiplied by each other divided by the square of the distance between their centers of mass. You include in the product this gravitational constant, and you will get an equality. And this gravitational constant is the same throughout the universe. Although our force of gravity on an object like us depends on where we are. The force of gravity on us, if we were on the moon, is very different than if we were on the Earth. But the gravitational constant is the same everywhere. It's constant. So look, let's look and see what is the force of gravity on an 80 kilogram human. A human who's got a mass of 80 kilograms. Let's see what the gravitational force of the Earth on that person is. And so we're going to use this equation that we've got right up here, and we have the force of gravity is equal to the gravitational constant. Let's put that down at 6.67 times 10 to the minus 11th, a very, very small number. The units for this are meters cubed, kilograms to the minus 1, which is the same as 1 over kilograms, times seconds to the minus 2, which is the same as 1 over seconds squared. And we take this value, multiply it by the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. Again, this is a very big number. And then multiplied by the mass of the object that's having the gravitational force affecting it, the human, 80 kilograms. And we're going to divide that all by the radius of the Earth, because that would be its center of mass. And the center of mass of the person, although it's not at where its feet are, the slight difference of, say, 1 meter compared to the 6.38 times 10 to the 6th meters is totally inconsequential. So let's put this down. So we have 6.38 times 10 to the 6th meters, and we're going to square that value. Now we're going to crunch the numbers with the calculator, and we're going to see what the force of gravity on this human is. What is the F of G on this human? Let's bring in our calculator. Let's turn it on, and we're going to type it in. We're going to see how to do this. We put in 6.67, To do the scientific notation, we're going to hit the second key, then hit the where it says EE, that's for base 10 exponent, 10 to the negative 11th. You use this negative. It is not the minus function, the negative 11. And then we're going to multiply that by the mass of the Earth, which is 5.98. Again, for the exponent, scientific notation, we hit the second key, then we hit EE. The exponent comes up. The exponent here is 24th. We multiply that by 80 kilograms. And let's get the product of those numbers before we do the division of the denominator. So we have 3.19 times 10 to the 16th. And we're going to divide that value. So I'm going to hit the divide key. And see, this word ANS comes up, which means answer. This is the answer, the 3.19, so on and so forth, times 10 to the 16th. That's the equivalent of this ANS answer. Divide by, then we're going to put in the radius of the Earth, 6.38. Again, we're going to do scientific notation. Second, EE, 10 to the 6th. And then we're going to square this value, and we're going to hit the x squared key. And you see this comes, the exponent squared comes up, and it squares this whole value, 6.38 times 10 to the 6th. The whole thing is getting squared. We hit enter, and we are left with 783, and we're going to do it to the hundredth, so it's 9. The next value is 2, and we look to the, and that's, we're going to leave it here, so we're going to look to the next position to the right, and it's 7, so we're going to round up to 3. Now let's see what our units are. We have meters cubed here. Down here we have meters to the second power. So we're going to cancel these meters squared, and we're going to get rid of 2 of the 3 meters up here. So we're left with meters. We have kilograms to the negative 1, which is the same as 1 over kilograms. And then we have kilograms times kilograms. So one of these kilograms cancels with this kilogram. We're left with a kilogram here. We're left with a meter here, and we have 1 over second squared. So that is kilograms times meters over second squared. Well, what is kilograms? Well, kilograms is mass, and m over s squared. I hope you realize that that's acceleration. Well, all forces are equal to mass times acceleration. Well, mass is kilograms, acceleration is meters per second squared. So those are the right units. Now, because the person who came up with these laws was a guy called Newton, kilograms, meters per second squared are the actual SI units, but this is also called newtons, which is a capital N. So now let's look and see what we've got. Put that over there. So this person standing on the surface of the Earth, 80 kilogram person, has a force of gravity from the Earth acting on it of, in the terms of 783.93 kilograms meters per second squared, or 783.93 newtons. Now let's look and see what kind of force of gravity the Earth applies to this double-decker bus. What's the mass of the double-decker bus? It is 6,600 kilograms. A little different from the 80 kilograms. So if we have force of gravity is equal to gravitational constant times, and here we're doing gravity, so it's mass of the Earth times, here in this case we'll say mass of the bus, divided by the distance between their centers of mass. And again, the bus center of mass may be more than a meter off the ground like the humans, might be 2-3 meters off the ground, but compared to the radius of the Earth doesn't mean a difference. So we are just going to use for this r, the radius of the Earth. And again, this r doesn't mean radius, this r is the distance between these two masses' centers of mass. And for the Earth, the center of mass is at the center of the sphere of the Earth. So let's see what we have for the force of gravity acting on this bus. Not the phone booth, the bus. So let's look again and see what is the gravitational constant. It's 6.67 times 10 to the 11th. So we're going to write here 6.67 times 10 to the 11th. What are those crazy units? They are meters cubed, kilograms to the -1, seconds to the -2. See that one more time, meters cubed. So we've got meters cubed, kilograms to the -1, seconds to the -2. We're going to multiply that again by the mass of the Earth. That's 5.98 times 10 to the 24th. 5.98 times 10 to the 24th kilograms. Now, instead of 80 kilograms, here we've got times 6,600 kilograms. I would say that's a significant difference. Let's divide that by the radius of the Earth. What the heck is the radius of the Earth? 6.38. 6.38 times 10 to the 6th meters. Let's just make sure I got the exponent correct. Oops, got lucky. It's correct. Now, again, it's r squared, so we square this. Let's bring in our calculator and see what we've got. Now, one wonderful thing about these calculators, we've already put all this in. The only difference is the mass of the object that the gravity is affecting. Well, we can go up here and get that first equation. Go back up here, and where the heck are we? Let's see, where do I want to be? 6.67. I'm going to hit enter here. The only difference is I just bring this back down, and I'm able to use this again. All I have to now type in is 6,600 for the kilograms, hit enter, and now I've got a new product for the top. I already had this in the calculator. I had 80 kilograms in, and I deleted the 80 and put in its place the 6,600. And so now I'm going to divide that again by the radius of the Earth squared. And that is 6.6. Whoops, I can easily cancel that. 6.38. Get rid of that. 6.38 second EE to the 6th. And then square that. And let's see what we get. Wow. Now we've got the force of gravity on this bus of 64,673.98 kilogram meters per second squared, or newtons. Remember, meters squared cancel with the 3 meters up there, and we're left with 1 meter. This 1 kilogram cancels with this one. We're left then with meters, 1 over second squared, kilograms, which is kilograms meters per second squared. So now we see that the force of gravity is very different depending on the mass of the object that the gravity is affecting. This 80 kilogram person has a gravitational force of 784 newtons acting on it, whereas this bus at 6,600 kgs, it's got 64,674 newtons acting on it. That is a huge difference. You could roughly say that the person, it's close to 1,000 newtons. The bus is over 64 times as great a force. Now, remember, all forces acting on an object will make that object accelerate as long as that force isn't zero. So, let's see what happens to this person and the acceleration that the force of gravity puts on it. And that's just simply F net, total forces acting on an object, and let's just say the only force acting on that person fell out of an airplane. Well, the only force acting on it, if we disregard air resistance, would be the force of gravity. Well, all net forces acting on an object make it accelerate. So we say F net equals mass times acceleration. Well, we've got a force of gravity on that person of 783.93 newtons. Well, this is 783.93 newtons. Let's just double check. Did I do that correct? 783.93 newtons. Let's see. What would be the acceleration, and in this case, due to gravity, be on that person? Well, I've got mass times acceleration due to gravity is equal to this 783.93 newtons. And if I want to know what the acceleration due to gravity is, I guess I divide both sides by the m of the person. Oh, that should be m sub p here. M sub p, m sub p. Well, I'm going to divide both sides by m sub p. The m sub p's on that side cancel out, and I've got the acceleration due to gravity is equal to 783.93 newtons divided by 80 kilograms. And in fact, you know what? Let's get rid of these newtons and let's put in some good units. The actual units, which are kilograms times meters per second squared. And if we do the division here, kilograms divided by kilograms, they cancel out, and we're left with meters per second squared, which is good because that's what we've got. We're looking for acceleration. Let's bring in our calculator, and we have 783.93 kilograms divided by kilograms meters per second squared, divided by 80 kilograms. And that equals 9.7999. We'll round it off to the hundredths. So the 9 gets brought up to a 0. It's 9.80 meters. What is that dot doing there? 9.80 meters per second squared. That's the acceleration due to gravity acting on that person of 80 kilograms. Now, what do you think the acceleration due to gravity is acting on the bus, which has so much more force of gravity on it? Huge difference of force. 64 times as great a force. What do you think the acceleration due to gravity will be on the bus? My gosh, it's a huge difference of force. Boy, I can't imagine that it's going to be, I don't know, that acceleration due to gravity on the person, well, the force of gravity on them is only 783 newtons. I just don't know. Well, let's see what happens. So again, the net force acting on an object is equal to the mass of that object times the acceleration of that object. And in this case, it's the force of gravity. So the acceleration will be to the gravity. How about if the bus fell out of an airplane? Wow. Well, let's go back and see. What was that force of gravity on the bus? 64,673.98. Remember that for me. 64,000, forgot it already, rat. 673.98 kilogram meters per second squared. And that is equal to, was it 6,600? I think it was. 6,600 is equal to 6,600 kilograms times the acceleration due to gravity. Now, let's see what the acceleration due to gravity is. Circle what we don't know. Get rid of everything else. And let's divide both sides by 6,600 kilograms. 6,600 kilograms. They cancel. The units here, kilograms and kilograms, canceled. We're left with meters per second squared. Can't imagine how big the acceleration on this will be since the force is so much larger. And so, you know what, let's go back and go up and get that 64,000. We'll take it right out of the calculator. See, all I do is move up this cursor. When I highlight what I want to bring down, I highlight it, then I hit enter, and sure enough comes right back down. Don't have to retype all that. Hit the divide key and key in the mass, 6,600. What do you think it's going to be? Got to be a big number. Let's hit the enter key and see. Holy smokes. The acceleration due to gravity on that bus is 9.80 meters per second squared. How the heck is that possible? And why is that? Well, it seems like that means that the mass has nothing to do with the acceleration due to gravity. Well, I'll let you in on a little secret. Not so much a secret, but let's remember our equations. The force of gravity is equal to the gravitational constant, and in this case we're talking about the mass of the Earth times the mass of some other object, person or bus. You know, we'll call it person and bus, or peanut butter, divided by the distance between their two centers of mass squared. Now, I'm not saying the mass of the person and the bus. I'm just saying the mass of the person or the bus really doesn't matter. Well, force, the net force on an object always equals the mass of that object, so we're going to say P or B, times the acceleration due to gravity. Now, look at this equation for a second. Now, I know the force of gravity equals this term. The force of gravity also equals the mass of the object that's having the force of gravity acting on it and its eventual acceleration. So the force of gravity equals this gravitational constant times the mass of the Earth times the mass of whatever object the gravity is acting on divided by their distance between their centers of mass squared, and that equals the mass of that object times the acceleration due to gravity. Well, let's just look at this part right here for a second. Now, if we wanted to simplify this, what's the same on both sides? You're right. The mass of this object that the gravitational force is acting on is on both sides of the equation. So we can divide both sides of the equation, put it over here, divide both sides of the equation by this mass, not the Earth, but the other mass, and look what happens. They divide out. So basically, by the mathematics alone, it shows you acceleration due to gravity, the mass of the object that the gravity is acting on does not matter. It falls out of the equation. Now, did the math demand that that was what happens in reality or in nature? No. Scientists observed this. Newton observed this, that the masses didn't matter. Galileo observed this. And then the mathematics bore out the same truth. Isn't that fantastic? Now, the funny thing is, or the question should be, how is it that two objects of enormously different masses and enormously different forces of gravity acting on those masses have the exact same acceleration? Now, we saw how the mathematics works, that the masses that have the gravitational force acting on them fall out of the equation. But why is it that that's the case? You've got this one force of gravity acting on this 80-kilogram person of 783 newtons, and then you've got a 6,600-kilogram object that's got an enormously different force of gravity, 64,000 newtons acting on it. Why is it that they accelerate the same besides the math that we just went over? Well, if we recall Newton's first law, which was his first law, which talked about inertia. What was inertia? Inertia says that all masses resist acceleration. They do, if they're in motion, they want to stay in motion. If they're not in motion, they don't want to be put into motion, and they don't want to be turned unless acted upon by an outside net force that's not zero. And so, and it also said, besides that, it said, the greater the mass, the greater the inertia. What does that mean? The greater the resistance to being accelerated. So in those terms, it kind of makes sense, or not kind of makes sense, it does make sense that since the person has a mass of 80 kilograms, a certain force on it will accelerate it a certain amount. But then a object such as the bus of significantly larger mass, to accelerate it to the same amount that the person is accelerated, it would take an enormously larger force to accelerate it to the same amount because it has so much more mass, which means it has so much more inertia. And what's inertia? The resistance to acceleration. And what are we talking about? The acceleration due to a net force. So if you've got a greater inertia, you need more force to accelerate that object to the same acceleration rate as something of much less mass. And so Newton's first law explains why the force of gravity is very different on objects of different masses, and yet their acceleration comes out the same. It goes a long way to explaining that all objects accelerate towards other masses at the same rate. It has to do with the fact that their inertias are different, all due to their mass.